Hello, I'm Jim Johnson, Sales Manager for Micro Measurements. I'm going to chat a bit today about gauging plastics, and more specifically 3D printed plastics. They need to have special handling due to their chemical sensitivity. And what we have here in front of us are the basic materials used for applying a strain gauge to plastics. And FUTech Advanced Sensor Technology kindly provided a series of test coupons for us that were 3D printed, and so we're going to use one of those today to demonstrate the proper handling, surface prep, and gauge installation techniques on 3D printed plastic. So the first step in any of the cleaning processes is to have all of the materials laid out that are going to be necessary for the surface prep. Plastics, being sensitive to solvents, typically get degreased carefully with isopropyl alcohol. The M-Line GC6 is a perfect choice for that. It's a high-grade, high-purity alcohol. Final cleaning is typically with the M-Prep Neutralizer 5A. We're going to be using a CEA series strain gauge today because plastics are sensitive to heat. We're going to use a pre-cabled gauge so that we avoid the heat of soldering. For our wiping and cleaning processes, we're going to use some surgical gauze, some cotton-tipped applicators. For surface abrading, we'll use silicon carbide paper, and I'm going to use the ATS-2 tool set, some of the tools out of that. And then we're going to be doing a checkout using our P3 strain indicator recorder. The first step in any process is cleaning anything that's going to come in contact with the strain gauge. So I'm going to start using a gauze sponge and a little bit of the neutralizer to clean the glass work surface that I'll use for prepping the strain gauge. So a few drops of the neutralizer on the glass. I'm going to scrub it vigorously to make sure any fingerprints or any particulate contamination has been removed. Then I'll fold that gauze over, wipe it dry with a single pass, and I'm going to set that glass aside until I'm ready for it. The next thing that I want to clean will be my tweezers, because they're also going to come in contact with the strain gauge. So I'm going to use a pair of blunt nose tweezers. These are precision ground so that they won't damage the strain gauge, and they're available through our accessory catalog. I'm going to clean that with a little bit of the neutralizer on a gauze sponge. I'm going to wipe the tips both outside and inside, and I'll splay the tips apart. Put the gauze sponge between the tips and draw it out carefully. This not only cleans it, but also checks for any damage, any burrs that might be on the tip that could hurt the strain gauge. And I'll set those aside over there with the glass plate until I'm ready. So the next step is to actually degrease the 3D printed plastic. So I'm going to use some of the GC6 alcohol and a gauze sponge. Now I'll dampen that gauze sponge with some of the alcohol, and I'll scrub my gauging area. And then I'll also clean the opposite side just to help ensure there's nothing that'll migrate onto the top surface. Most 3D printed materials tend to have some texture. As this is built up by the printing process, the surface tends to be a little bit irregular. This is not too bad, and we can make this more uniform just with the abrading using the silicon carbide paper. If it was more irregular, we might have to use a combination of abrading and filling with something like our M-Bond AE10. So I'm going to start with some 220 grit silicon carbide paper just to help remove some of these irregularities on the surface. So I'm going to sand this entire area that I'm getting ready to prep for the gauge installation. And I'm really looking for just a change in the surface finish so it goes from gloss to a matte finish. I don't want to appreciably thin the material. I'm just trying to make it more uniform and create some mechanical tooth for the adhesive to lock into. After the 220 grit, I'm going to go to 400 grit. to get a little finer surface finish. And about 10 strokes back and forth is sufficient. We've eliminated that gloss finish. It looks very, very uniform and should do a very good job accepting the strain gauge installation. So the next step I'm going to use is I'm going to scrub this with some of the neutralizer. Now on most metals we'd be looking for a nice uniform wetting of the surface, and it looks like this plastic is wetting very nicely as well. The chemical's not beating up on the surface at all. So I'm vigorously scrubbing with the neutralizer, and it's important that there's sufficient chemical present so that it doesn't evaporate during the scrubbing process, because any contamination or loose material, we want it to stay in suspension so that we can absorb it. We don't want it to evaporate and redeposit on the surface of the test specimen. So once I'm happy with my scrubbing, I'll take a clean piece of surgical gauze, fold it into quarters, and I'm going to wipe with a single pass, but I'm not going to wipe from the contaminated area that I haven't cleaned into the prepped area. I'll start about a third of the way inside the prepped area, wipe with a single pass in one direction. Then I'll fold that over and wipe in the opposite direction, again starting well inside the prepped area and wiping off the far end of the coupon. Now with most metals we would use a 4H pencil or a ballpoint pen that's out of ink to burnish an alignment mark. Being that this is a white material, it's going to be a little difficult to see a burnished mark. So I think what I'm going to use is a little bit of ink, and I'm going to mark it outside of the actual gauge area. So I'm going to use my steel scale, and for the purpose of this exercise I'm going to come about 4 inches in from the end of the coupon, and I'm going to put a little mark on each side near the outer edge, outside of the gauging area. Next, I'm going to prepare my strain gauge. So I'm going to slide the test specimen up out of the way a bit, take my glass plate that I previously cleaned with neutralizer, and then I'm going to take my pre-cabled, my C2A series strain gauge, and remove it from the package, and carefully take the gauge out of the plastic folder and place the strain gauge on the piece of glass. Now, bonding a pre-cabled strain gauge is a bit more of a challenge than bonding an uncabled gauge, but again, I'm going to try to avoid any damage to the coupon that might be induced by the application of the heat of the soldering iron. So now I'm going to take some of the PCT 2M gauge installation tape. I'm going to pull off the first couple of inches that might be contaminated. Discard that. I'm going to fold over a small handling tab on the end of the tape, and then pull off a 5 or 6 inch long piece. Give it a little tug so it doesn't curl up. And then I'm going to lay that tape over top of the strain gauge so that I can use the tape as a tool for positioning the gauge on the test specimen. Now I want to put a corresponding mark on the tape that I can use as a reference relative to the marks that I placed on the test specimen. So I'm finding the alignment triangles on the sides of the strain gauge, and I'm going to transfer those out here onto the tape. Again, outside of the gauge area. And then I'll use that as a reference for placing the strain gauge on the specimen. So to avoid damaging the gauge, I'm going to lift the tape at a shallow angle, ideally 45 degrees or less, to remove it from the glass. And then I'm going to transfer the gauge tape assembly over to the test article. So I'm going to visually center it side to side. I'm going to use the alignment marks on the tape for placement. And now the tape, I'll be able to hinge back to get to the gauge site for application of the adhesive system. For bonding, we're going to use the M-Bond 200, which is a high-grade cyanoacrylate adhesive. And the kit consists of a catalyst and the cyanoacrylate adhesive. So I'm going to expose the back of the strain gauge by lifting the tape at a shallow angle. And I'm going to pull it back at least 1/4 of an inch, maybe a bit further. This will allow me to apply catalyst to the back of the strain gauge and adhesive to the test specimen. It's important to put a very minimal amount of the catalyst on the back of the gauge, and the proper technique is to blot the brush inside the neck of the bottle 10 times before applying the brush to the gauge. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to hold the brush parallel to the back of the gauge, not perpendicular. And I'm going to start on the tape, wipe across the back of the strain gauge, go on out onto the tape away from the gauge before I lift. It'll tend to leave a little bit of puddle of catalyst, and we don't want the puddle on the back of the gauge. The catalyst consists mostly of alcohol as a carrying agent, and the carrier has to completely flash off before we make the bond. So we're going to wait a minimum of 30 seconds for the alcohol to flash. Then we're going to apply the adhesive not to the gauge site but outboard of the gauge site. It's important that we place the adhesive away from the gauge site and then squeegee the gauge in place to wash fresh adhesive across the gauge site. The adhesive will react to the atmosphere almost instantly and begin to cross-link, and we want to avoid a thick bond line. So by putting it outboard of the gauge site, squeegeeing the gauge in place, we wash fresh adhesive across the gauge site right as the strain gauge arrives at the location. So we've had sufficient flash time, so I'm going to take a couple of pieces of gauze. I'm going to fold one into quarters. That'll become my squeegee. Another one will catch a few drops of adhesive that I'm going to discard just to ensure I have fresh adhesive. Anything in the tip might be contaminated. So I'm going to dispense 2 or 3 drops into this piece of gauze and discard it. Now I'm going to place a drop of adhesive on the beam in line with the strain gauge but outside of the strain gauge site. I'm going to use my tape to hinge the gauge back over in place and use a gauze sponge to squeegee that to create a very thin glue line. And then I'm going to apply my thumb as a mechanical clamp for 1 minute. The pressure from your thumb as well as the heat The warmth from your thumb helps kick the reaction off. It's important to remember that cyanoacrylate adhesives have a strong affinity for bonding flesh. So if you accidentally use too much adhesive or get any adhesive up on top of the tape, between the tape and your thumb, don't try just pulling the thumb away from the test specimen. At the end of the 1 minute, you want to press down very firmly and rotate your thumb 180 degrees to shear any adhesive that may be between your thumb and tape so that you avoid tearing flesh off your thumb. Alright, so I've about reached my 1 minute. So in preparation of removing my thumb, I'm going to press down firmly, rotate my thumb 180 degrees. And now typically we'd wait another minute to give that adhesive a complete opportunity to cross-link. In the interest of time saving, I'll get the cable ready to connect to the instrument. We're going to use a P3 strain indicator recorder. It has all the bridge completion built into it. This is a 120 ohm strain gauge. Encoded into the part number is the resistance, and it's also listed higher up on the engineering data label. We always use a 3-wire quarter bridge, hence the 3-conductor cable, red, white, and black. When we make the connections to the instrument, red will go to positive excitation, white will go to negative signal, and black will go to the dummy resistor of the corresponding resistance to the strain gauge. So I'm going to make those connections here on the P3. Positive excitation is labeled as P+. White is the negative signal, or S-. And the black lead completes the bridge by connecting to the what we call dummy resistor of the same value as the strain gauge. It's in the adjacent arm of the bridge circuit. And so now we've got the strain gauge connected to the instrument. It also interfaces to the laptop computer so we can have a display on the laptop. All right, with the strain gauge now connected to the P3 and the P3 interface to the computer, we've given ample time for the M-Bond 200 to fully cross-link. I can now remove the gauge handling tape, and I make sure I fold it back over itself because I'm trying to break the bond between the tape mastic, the adhesive, and the substrate. Extra attention has to be given when pulling the tape off of the lead wires to make sure we don't pull those off the strain gauge. And now it's important to put a little bit of a service loop in those fine transition wires. So with a little extra care and handling, we can sort of decouple the cable from the substrate. With that little service loop, I'll take a piece of the gauge installation tape and I'll tie the vinyl insulated 3-conductor cable to the 3D printed beam just to give us a little protection from any tugging or pulling that we might do to that cable. And then what we want to do is do the checkout. We look for a couple of things. First, 0 stability, and then 0 return. Now, this being a 3D printed plastic, it's probably not going to have good spring properties, but anyway, we'll make sure that we're interfaced to the instrument, everything's working there. We're going to have an initial 0 offset that will balance out once we get the beam cantilevered off the side of the table here. And you can see that initial 0 output on the display of the P3. And so we'll position the beam so that the gauge is just off the edge of the table in a cantilevered fashion. We'll 0 balance the initial 0 offset and look at 0 stability. Then I'm going to apply some load, remove that load, and look at the zero return. If the gauge does not come right back to zero, that's indicative of plus creep in the 3D printed plastic. If this was a good spring material like 2024 T4 aluminum, we would expect excellent zero return, even within one or even less counts. But we're seeing not only some failure to return, but you'll see over time the installation slowly creeps back to zero. If this had passed through zero and been a negative value, that would have been indicative of negative creep in the installation, but being this is showing a positive offset that's slowly counting down to zero, that indicates plus creep in the substrate material. So the gauge is following the material. It's telling us what's going on in the plastic. So now to further illustrate this plus creep, put a little static load on it and look at the output over time. And you can see that that output is increasing with time under a static load, again indicating that we're seeing plus creep in the plastic. The strain gauge is not lying to us. It's telling us the truth of what's actually taking place in the substrate material. So to sort of summarize, we can install strain gauges on 3D printed plastics. The plastics, of course, oftentimes are not going to be good spring elements, but as 3D printed plastics become more common as an engineering material or prototyping material, we're going to expect to have to use strain gauges to characterize the performance of that material.